it can sometimes be useful to consider electric fields and potentials in terms of equipotentials or equipotential surfaces. As the name indicates, an equipotential, equal, and potential is potential. So an equipotential surface is a surface over which the potential is equal. This, I don't know if you've studied them, but this is a similar concept to topographic maps. You know, where you have a hill and a given line on the map is a line of equal elevation, and then so you know, hills and mountains wind up being concentric or not quite concentric rings of these lines, and equipotentials are a similar concept. Along a given line, the electric field is, or the potential is a constant. And if the potential is constant along a given line, that means there's no electric field in that direction, meaning the electric field is perpendicular to an equipotential surface. We know a change in potential is equal to minus E over delta S, and that's where the perpendicular part comes in, that our minus E times delta S. Sorry, the change in potential is minus E times delta S, right? Where delta S is a displacement in the direction of the electric field. Well, if this displacement then is perpendicular to the electric field, then there is no displacement in the direction of the electric field, and the change in potential is zero. So the E field is perpendicular to an equipotential. The E field, we kind of already know this. The E field points in the direction of decreasing potential. That is, if the electric, we know that the delta S is positive in the direction of the electric field, and therefore if we have a positive delta S, then we wind up with a negative change in potential. And I just realized I didn't write the word potential. So the E field points in the direction of decreasing potential, and as I said, the electric field is perpendicular to equipotentials. So let's think about this. You know, if we have a point charge, we know what our electric field looks like. We know that it radiates straight out. Maybe radiate isn't the right word, but it points straight out in every direction. And then our equipotentials are going to be perpendicular to the field at any given point. So in the case of a point charge, since the electric field is radially symmetric, then the equipotentials are going to be, this would be an equipotential line, and then there would be concentric spheres. They're circles on the paper, but they would be concentric spheres because then they're perpendicular to the electric field at every point, and each point along this thing has the same radius, and the electric field is related to radius. And if the electric field has the same magnitude at a bunch of different given points, then those points will have the same potential as well. As you go perpendicularly around this circle, there is no displacement in the direction of the electric field or against the direction of the electric field, and so the potential remains constant. Another example, if we have a parallel plate capacitor, we've got a positive one on top, positive plate on top, got our negative plate on the bottom. We know the electric field points this way. In between, it points straight down. In this case, our equipotentials, they run perpendicular to the electric field, so in this case, they would be horizontal. And they wouldn't be closed surfaces in this case, because the electric field outside basically doesn't exist. So they're just the equipotentials are just horizontal lines in that case. A conductor, we know that on the surface of a conductor, the charge is evenly distributed because the electric field is perpendicular, always perpendicular to a conductor, whether it's going out, if there's some positive charge inside, it might be going outward, or depending on where it's at, something different might be happening. But a conductor's surface is always an equipotential, because if it wasn't an equipotential, then the charges on the surface would move around until it became an equipotential. And we know the electric field is always perpendicular to the conductor. And therefore, conductors are always equipotential surfaces. A few applications of potential differences. There are a few medical things. An EKG, which stands for electrocardiogram. An electrocardiogram has a C, so I don't know why this is called an EKG instead of an ECG, but it is what it is. And an EEG, electroencephalograph. The EKG is for the heart. The EEG is for the brain, I believe. And they measure the potential differences in the heart and brain, which allows doctors to diagnose various illnesses or check for all sorts of different medical things that can happen in your heart and brain. And I just think it's, there are these potential differences in our body, and I think it's really cool that God has created us in such a way that we can observe and measure these things that are going on inside the body without damaging ourselves.